C1, C2, should be C3, CK. And I link them to each other. Complete click, K click here. Now from coloring problem we know that if we have K click, they all must have different color, right? So impossible. So from that, because I have a K click, I know that K colors will be needed at minimum. So I can't survive less than K colors. Then I will make one extra link, extra node here, what I call false color. It's just a name, false color. It could be just I have a red, green, blue, yellow, whatever here. Here I make, let's call it like a black. Is black a color or not? So it's a definition, but yeah, I call it false color. So now you can see that I try to build this connection between the Boolean equation and the coloring. So any other colors are kind of true colors then. Okay, and then my equation, they have the variables. Okay, here they are called literals. So I have up to, okay, according to here we have x, yeah. I have feeling there are a little bit bugs, at least here was bugs, so I'm sure should this be n here. I think this should be n because we have n variables. So I make one node for each, two nodes for every variable. And one I will represent the x1 is true. And the other one represent the x1 is false. And I connect them to each other. And now I will color the algorithm which will solve this problem. It will color x1 and not x1 with two different colors. Because they are connected, they have to have different colors. And then I will connect this x1, I will connect it to C2, C3, C4 and everything up to CK, except C1 I don't connect. So now this no, this has to be K because it has to match into this color node. So the number of variables and the number of colors have to be matching. So I connected to all other except this one, and now it means that x1 or not x1, one of them I can color whatever color will be here. So remember, all of them has to have different color. So all the true colors, red, green, blue, yellow, and so on are here. So whatever color is the color number 1, because this is not linked here, I can use this color to one of them. So if this will be blue, I don't know does it look like blue or not. So if it's blue, then I can color one of them blue. Doesn't matter what, I have two choices. It's like non-deterministic Turing machine, now you make your choice. But because this link exists, the other one has to have different color. But also, because it's connected to all other color nodes, it cannot have any other true color. So the other color must be, only then it's not connected with the false color, right? So this has to be then the false color here, or vice versa. So two ways of coloring these nodes is one of they have to matching color here and one to have matching color from here. And this coloring choice is free to choose here. And this will represent, if this will be the true color here, in this one, then it means that x1 variable in the equation is true. If the not x1 will have the true color, then it represents that the x will be false in the equation. So the coloring choice is equivalent to the choice of the variable in the equation. And okay, so I forgot to say that both also the not x is connected to all of these color nodes. Both of them are connected to the color nodes, all except this C1. So then x2 is the same way, it's connected to C1, C3, C4, but not to C2. And same for not x2. x3 is connected to x, C1, C2, C4, 5, and so on, except C3. So every pair of these variables, one of them can take the true color of the corresponding index here, and the other one has to take the false color because of the connections made. Okay, so now I have created that I have a Boolean equation and I have a graph, and the coloring of the graph and the choice of the variables are equivalent. So I have freely choose any variable combination what I want. But now it is not enough, because now I can choose any combination and I can color it by k colors, right? Oh, sorry, k plus 1 colors. Yeah, so I think the question is, can we color it to k plus 1 colors? So that's the, because we have one false color. So we have k plus 1 colors. And now finally I want to add the actual Boolean equation, because now the Boolean equation has these terms. Okay, just a question. What is the time? Puoli. 4.
Yeah.
Oh. Okay, puoli in Finnish means half. Okay, so then let me. I just looking. Oh, still 50 minutes time. Then I was still 50 minutes time. So I seem to have plenty of time. Okay, so now this equation, it was like x1 or not x2 and so on. So this is the one term f1, so it consists of this. Now modeling this equation, I make of these terms, I make one node of each of the terms. And whatever variables are in this term here, in this case it has x1 or not x2. So what I do, I connect this to node to all but those retailers that are in here. So I connect it to all of these nodes. Okay, x1 is there, so I'm not connected to x1. So basically it means that this can have the same color what is here. But I will connect to here, not x1, then I will connect to, okay, not x2 is there, so this one connection is missing. So that color it can also have. So these are kind of the nodes, these are here in this equation. So connection of these are cut away. It's allowed to use whatever color these two have. But all others are connected, so basically it prevents this node cannot have the color of what is here. It cannot have color what is here. It must have color. It must have either color of C1 or C2. And now it corresponds to what makes this true. Of this will make true if x1, so either one of them has to be true. So, and this corresponds that either one of them must have true color. So you can choose any variable combination you want. So you color these nodes first, but then I will color this one. I have to choose one of them. And if you have used the true color of one here and true color here, you are only left the false colors here. I have only choices to choose false color, right? But the last trick what I do, I will make a connection to the false color. That prevents me that I can never use false color in my function if this term here. And as a result, I can only color this using the existing k plus 1 colors only if you have set such variable combination that true color, either this one has true color or this one has true color. If one of them is available, then I can color it. Otherwise, I would need k plus 2 colors. And this way, I model all the FEs, I build all the FEs, makes the connections, and it forced me to choose. And I will find the coloring only if the corresponding equation will be satisfiable. Okay, that's a technique. The length of the equation is whatever is the length of the equation. You can calculate how many nodes I will be needed. So the number of variables times 2, the number of terms plus the number of terms. Okay, actually it's the number of colors, number of variables times 3, because I have the color nodes, the true and the false. The number of terms plus 1 for the false color. So this is like linear. Whatever is your length of your, okay, how many variables you have, I have linearly dependent of number of nodes in my graph. So the conversion from the equation to the graph takes polynomial time. And now, if I have an algorithm to solve the coloring for this graph, and you have the satisfactory problem, give me your equation, I make a graph, then he has there with the window. He has a good access of good algorithm to solve the coloring problem. I will ask you, okay, this is my graph. Can you color it by k+1 colors? And then he says, or he says no. And then I come to you, your equation, if he says yes, I say yes, your equation is satisfiable. Then you have another equation, okay, he says no, this I make a graph and ask, can it be colored? He says no, cannot be colored. And then I come to you and sorry, your equation cannot be solved. It's not satisfiable. So there's an equivalence of this, so we can, but only one way, from here to here. This doesn't give the vice versa, because vice versa is that any graph could be connected to equation. This is not, I'm not showing that, I'm showing for any equation, Boolean equation can be converted to graph coloring problem. Okay, let's continue tomorrow, next week, so that we have last week, next week. There will be Monday. I will complete this within about 1 hour. Give example of this and the other example. Then I continue question and answers in Joensuu. So if you have any questions considered any part of the lectures so far, so prepare questions. If you send it to me beforehand, I can prepare. If not, I will deal with it only if time. And then Kuopio, are you still there? Tuesday.